Welcome to the debate. If you take a standard party balloon and blow it up here in the studio, it is an almost effortless exercise.
Right. Yeah, just regular air.
Exactly. The rubber expands, the air fills the space, and it pushes back against the atmosphere with this soft, predictable elasticity.
Because it is highly compliant. The air is forgiving, you can squeeze it, twist it, and it just kind of moves out of the way.
It does, but if you take that exact same balloon and attempt to inflate it 800 meters below the ocean's surface, the physical reality completely flips. You are not pushing against 1 bar of atmospheric pressure anymore.
No, you are pushing against 80.
Right, 80 bar. Confined under that sheer hydrostatic weight, that same volume of air no longer behaves like a soft cushion. It behaves like a violently coiled steel spring.
And that massive shift in fluid mechanics, the idea that extreme depth physically turns air into a rigid, almost solid wall, is really the fulcrum of what we are analyzing today.
Yes, it is. Today we are examining the 2026 formal concept paper by Zachary David Enfield. It is on the stepped pressure high bar oscillating water column, or the SPHBOWC.
Quite the acronym.
Right? But the central question we are exploring from this material is pretty clear. We are asking whether utilizing extreme deep ocean hydrostatic pressure, so up to 80 bar at 800 meters depth, is a brilliant architectural breakthrough that solves the persistent inefficiencies of surface-level wave energy, or if it introduces an insurmountable cascade of engineering impossibilities.
And just to set the ground rules, all of our discussion today will be grounded strictly in Enfield's 2026 paper and its cited research.
Exactly. So for my part, I will argue that the SPHBOWC elegantly synthesizes established physics and maturing adjacent technologies like underwater compressed air energy storage to fundamentally change the power density of marine energy.
And I will argue that the exact physics providing that theoretical advantage, specifically, the extreme stiffness of an 80-bar gas spring and the unprecedented cyclic fatigue required at that depth, create practical engineering barriers that make the entire system completely unworkable.
Okay, so to understand why this concept is even necessary to discuss, we first have to look at the economic reality of wave energy today. Right now, conventional surface oscillating water columns, or OWCs, are stuck.
They really are.
We have built them. We know they work. But they just do not make financial sense yet. The levelized cost of energy, basically what it costs to generate 1 kilowatt hour over the lifespan of the machine, remains totally pre-commercial for wave energy. We are hovering between 37 cents and $1.22 per kilowatt hour.
Which is incredibly expensive compared to something like offshore wind, which is pushing well below 10 cents.
Exactly. It is not even a contest right now. So if marine energy is going to meet the European Strategic Energy Technology Plan's target of 150 to 100 euros per megawatt hour by 2030, incremental tweaks to surface buoys just aren't enough. We need a radical conceptual leap to squeeze vastly more power out of the exact same amount of steel and concrete.
Well, sure, but a leap into 800 meters of water is quite the departure from a surface shoreline. You are moving from an environment where we can easily build and maintain things into literally one of the most hostile environments on the planet.
It is absolutely hostile, but the core genius of the paper is treating that hydrostatic pressure not just as a structural burden to survive, but as an active design variable to exploit.
To use it to your advantage.
Right. The paper relies heavily on what is called polytropic gas behavior. Let's unpack that for a second. When you compress a gas very quickly inside a chamber, the heat of that compression does not have time to escape.
It stays in the system.
Yes, and that drastically changes how much pressure pushes back at you. At 800 meters down, where the baseline pressure is already 80 bar, a tiny fractional volume change inside a trapped gas chamber produces an absolute pressure excursion 80 times larger than it would at the surface.
Meaning, if you push the water up even just a little bit, the air pressure absolutely skyrockets.
Yes. If a wave forces a water column up by 1 meter at the surface, you get a modest pneumatic push of air through your turbine. But if you force a water column up by 1 meter at 800 meters depth, that identical physical stroke yields a massive, hyperdense turbine driving force.
The multiplier effect.
Physics to do this. That is the beauty of it. It simply reorganizes verified subsystems. It takes the oscillating water column principles we have already seen working at the Mutriku plant in Spain, integrates the isobaric storage concepts from underwater compressed air energy storage UWCAES, and utilizes a dry turbine shaft situated safely above the high-pressure wet zone.
Look, I get it. The mathematical elegance of that polytropic relationship is undeniably appealing on paper. I mean, the idea that you get an 80-fold multiplier on your pressure excursion sounds like magic.
Because it is highly efficient.
But it contains a built-in fatal flaw. And the paper explicitly identifies this. It is the paired penalty.
You mean the stiffness of the air?
Exactly. The stiffness. As the baseline pressure increases by a factor of 80, the gas spring inside that chamber becomes 80 times stiffer. This extreme stiffness effectively freezes the water column piston. Think back to your balloon analogy from earlier. Because the air is fighting back with 80 bar of resistance, the water simply will not rise into the chamber.
It hits resistance.
It hits that pocket of air and bounces off it like it hit a brick wall. To get around this, the design requires an absurdly perfect system of compliance accessories, basically secondary air tanks and tuning valves, just to allow the water to achieve a basic stroke.
The compliance tuning is demanding, certainly, but it is an engineering optimization problem. We know how to move air between high and low pressure accumulators. It is complex plumbing, I will give you that, but it is not a violation of physics.
But it becomes a critical failure point when you factor in the operational tempo. The highest risk identified in the source material is the cyclic loading. You mentioned underwater compressed air energy storage.
Right, UWCAS.
Yeah, the problem with using that as an analogy is that UWCAS deals with very slow static charge and discharge cycles. You pump air into a concrete dome over a few hours, and you release it over a few hours. The SPH Boeing, by contrast, demands 0.05 to 0.2 hertz of continuous cycling.
Which is frequent, yes.
It is millions of violent, rapid-fire compression and expansion cycles at 80 bar. You are subjecting the dynamic gas-water interface to a catastrophic fatigue environment that simply has no precedent in current deep-sea engineering.
I see why you think that, but let me give you a different perspective on how the forcing mechanism actually operates at depth, because it directly addresses that piston freezing concern. If you are listening to this and thinking, well, how does a wave even reach 800 meters down, you are right to be skeptical. Surface waves attenuate exponentially. By 800 meters, the orbital velocity from a surface storm is effectively zero.
The ocean is still.
Right, it is calm. So the device relies on what Enfield terms Subsystem 1, the stepped intake geometry. Instead of a passive, wide-open aperture pointing up at nothing, the device uses directional abyssal scoops and check-valved surge inlets.
Wait, hold on, slow down. Let me make sure I am picturing this right. They are trying to capture deep sea currents instead of surface waves.
Precisely. The deep ocean is not entirely static. There are persistent internal tides and deep currents generally moving around 2 centimeters per second.
2 centimeters a second. That is barely a crawl.
It is slow, but it is a massive volume of dense water. By applying the continuity principle, the device trades the massive cross-sectional area of a wide intake for velocity at a constricted throat. It is exactly like putting your thumb over the end of a flowing garden hose to make the water spray faster.
Okay, I see the fluid dynamics there.
Right. The intake channels those slow, persistent ocean flows into a concentrated, repeatable hydraulic slug. This acts as an abyssal pulse piston, so the system is not relying on a continuous geyser blowing up to the atmosphere. It is rectifying a slow, heavy ocean movement into a sharp, powerful stroke to compress that dense gas spring.
I am sorry, but I just do not buy that. Let me tell you why. Think about the energy balance here. Try to imagine compressing a heavy-duty truck suspension system using only a gentle, persistent breeze.
But water is much denser than air.
It is, but even if you funnel that flow through a narrower tube to speed it up, the total energy in a 2 centimeter per second current is incredibly diffuse.
But internal waves, which occur at density stratifications deep underwater, carry significant concentrated energy.
They do carry energy, I agree, but coupling a 2 centimeter per second flow into a hydraulic pulse sharp enough to meaningfully compress a gas spring that is 80 times stiffer than one at sea level, that is an enormous hydraulic stretch. It is a fundamental mismatch of forces. Furthermore, look at the modularity issue.
The site specificity?
Yes, because the gas spring constant is entirely dependent on the ambient hydrostatic pressure of the water outside. The compliance volumes, those secondary air reservoirs meant to tune the system so the water can actually enter, they must be entirely re-engineered for every specific deployment depth.
Because the baseline pressure changes if you move it up or down.
Exactly. A device designed perfectly with the right air tanks for 600 meters physically will not operate at 800 meters. The spring becomes too stiff or too soft. You destroy the very modularity that makes manufacturing economies of scale possible. I mean, the reason solar panels and wind turbines get cheaper is because you stamp out the exact same widget thousands of times. If every single SP-HBOWC needs a bespoke internal pneumatic architecture based on the bathymetry of its specific location, the economics completely fall apart.
That is a really interesting point, though. I would frame it differently. Site specificity is a reality for all marine energy devices. You do not deploy the same offshore wind foundation in deep mud as you do on solid bedrock. We are already used to adapting to the seabed.
Sure, the foundations adapt, but not the core engine of the machine.
True, but let us look at the structural side. Because you're concerned about material fatigue and the machine shattering under this multi-cycle load, brings us to the near-future feasibility window of 2026 to 2032. The paper heavily grounds this concept in the rapidly maturing field of deep-sea structural engineering.
Which is advancing, yes, but mostly for static oil and gas applications. Like pipelines and wellheads, they just sit there.
Not exclusively. We are seeing incredible leaps in materials science that the SPAHOOW can directly utilize. Take 5A06 aluminum, for example. On the surface, salt water eats aluminum alive. It is terrible for it. But counterintuitively, if you drop 5 series aluminum down to depths of 500 to 2,000 meters, the dissolved oxygen levels in the water are so low that the corrosion process effectively starves.
Oh, wow, so it actually preserves itself.
Yes, the material actually becomes safer and more stable at depth.
That is fascinating regarding corrosion, I will admit. But what about the physical crushing force?
That is where the concrete comes in. We are seeing the emergence of geopolymers with 100 megapascals of compressive strength, offering ultra-low permeability for depths exceeding 1,000 meters. We even have the rise of additive, 3D printed titanium for pressure-neutral housings, achieving incredible mass-to-strength ratios. The point is, the SPHBOC doesn't have to invent these materials. It simply inherits these breakthroughs as they come to market over the next decade.
That is a compelling argument, but have you considered the fundamental difference between static pressure and the dynamic multi-cycle loading this machine demands? Because the context of those materials matters immensely. Deep-sea rock mechanics research cited in the material explicitly shows that confining pressure causes a brittle to ductile transition in materials.
Meaning the fundamental failure modes of the materials change at 800 meters?
Exactly. A material that gracefully bends or yields at the surface might catastrophically shatter under cyclic fatigue at 80 bar. You brought up underwater compressed air energy storage earlier.
Yes, the UWCAES systems.
Right. The Barrelmar pilot in Cyprus is a perfect example of this. It aims for a highly impressive 70% round-trip efficiency using static isobaric storage. But static is the operative word there. Barrelmar's concrete and steel tanks are resting on the seabed. They are not being subjected to millions of violent high-pressure compression expansion cycles from a wave-driven piston hitting them every 5 seconds.
So you are saying the fatigue life at 80 bar is a total unknown?
It is worse than an unknown. It is an active hazard. And when we look at sealing, which, by the way, the paper admits is the most demanding single engineering challenge, it gets even more precarious. To keep the pressurized air and the water separate, you need dynamic seals. The dual sliding radial seals we currently use work beautifully for small scientific viewports on manned submersibles.
Right, for small applications.
But scaling those up to maintain a dynamic gas-water boundary across a massive industrial chamber, moving continuously at 0.2 hertz, that is bordering on pure fantasy. The friction alone at that pressure would just tear the seals apart.
I am not convinced by that line of reasoning, mostly because it assumes we must perfectly master the 800-meter environment on day one, and that simply isn't how engineering works. The paper lays out a very deliberate, staged development roadmap that directly addresses these material and sealing risks.
You mean the phased approach?
Yes, the concept does not call for an immediate, reckless leap to 800 meters. Phase 1 proposes a 50 to 150-meter intermediate prototype. In engineering terms, this operates at a technology readiness level 3 to 5. It is essentially a scale model built to prove the plumbing works before you risk dropping the real thing into the abyss. At 50 meters, we are dealing with 5 to 15 bar, which is enough pressure to observe the polytropic multiplication effect, but shallow enough that regular surface waves still provide the forcing.
So you do not even need the deep sea internal tides for phase 1.
Right. Phase 1 allows engineers to safely validate the closed-circuit pneumatic buffer. They can test the high-pressure and low-pressure accumulators, verify the check valve timing, and critically, prove out the gas-water interface sealing over millions of cycles in a much more forgiving environment. Only after the radial seals survive at 50 meters do we scale to the abyssal depths.
Okay, I come at it from a different way. Phase 1 might successfully validate the pneumatic circuitry. I can concede that. But phase 3, the actual downstream commercial viability at 800 meters, that is where the economic reality shatters the concept. Let us look at the operational expenditures. The OPEX.
The paper openly acknowledges OPEX will be higher due to remote operations.
Higher is an understatement of massive proportions. Look, if you have a surface OWC, like the Matrico plant in Spain, a technician can literally just walk out onto the breakwater with a toolbox to replace a sensor or clear a fouled turbine valve. It is cheap and it is easy. For an 800-meter fixed installation, human divers are completely off the table.
Of course.
You need a remotely operated vehicle, an ROV, or a fully crewed work-class submersible for every single maintenance action. Chartering one of those vessels costs tens of thousands of dollars a day. That alone severely penalizes the levelized cost of energy we talked about earlier.
Which is precisely why the architecture places the turbine in a dry shaft much closer to the surface. By utilizing that closed-circuit pneumatic buffer we discussed, you decouple the high-pressure wet environment from the power takeoff. The turbine is the most complex, maintenance-heavy component in the system.
Right.
So in this design, it sits at 50 meters, it is easily accessible by conventional commercial divers, while only the highly durable concrete and titanium pressure chamber sits down at 800 meters, doing the dirty work.
That helps, absolutely. But the lower chamber and those highly compliant volumes still remain at 800 meters. If a check valve on the intake scoop fouls with biological growth, or if that giant radial seal on the compliance accumulator degrades, which, again, we establish is highly likely under multi-cycle fatigue, you are still chartering a deep-water ROV vessel.
That is a fair concern.
Furthermore, just finding a place to put this machine is prohibitively expensive. With surface wave energy, we have incredibly detailed, globally available surface wave energy atlases. We can look at a map and know exactly where the best wave energy is.
True, deep ocean forcing cannot be mapped from satellites in space.
Exactly. Identifying a site for the SPHOWC requires hyper-expensive deep ocean bathymetric and internal wave surveys. You literally have to send ships out to figure out if a location even has the right 2 centimeter per second internal tide to make the stepped intake work. You are incurring massive upfront site characterization costs before you even pour a single gram of 100 megapascal geopolymer. From day one, the LCOE is theoretically uncompetitive against offshore wind or even floating surface OWCs.
It is expensive to map the ocean floor, yes. But we are looking at a long-term trajectory here. A comprehensive factors analysis in the paper shows that marine energy across the board needs a 75% capex reduction, combined with the economies of scale from large arrays just to get below that critical 30 cent per kilowatt-hour threshold. Surface OWCs might never get there because they are limited by the low energy density of surface air.
They max out.
Exactly. The SPHBOCI offers a pathway to that cost reduction by radically increasing the power density per unit of structural mass. The theoretical foundation here is undeniably coherent. The physics of trading volume for extreme absolute pressure works.
On a fundamental thermodynamic level, yes. The polytropic behavior is sound, the math is real. I am not debating the math.
And it perfectly aligns with the marine energy sector's broader shift toward broadband capture and hybrid architecture. For instance, the system does not just rely on the deep ocean pushing from the bottom. The dry turbine shaft terminates at the surface with a wind assist vortex cap.
Ah, the aerodynamic component.
Right. By utilizing stack effect aerodynamics and ambient coastal winds blowing across the top of the device, that cap can actually pull air through the system. It reduces discharge separation losses and contributes 5 to 10% of the total airflow augmentation. It is not just a deep-sea wave energy converter, it is a fully integrated, hybrid pressure wave wind machine.
I will certainly acknowledge the conceptual elegance of decoupling the turbine from the direct force of the ocean, using a closed pneumatic circuit with high and low pressure buffers so the turbine sees a smooth, continuous, unidirectional flow of air rather than the violent, bidirectional sloshing of a wave transient. That is excellent engineering.
It solves a massive problem.
It elegantly solves one of the biggest historic problems in surface ODWs. But I maintain that the brutal reality of the abyssal environment offsets that elegance. The multi-cycle fatigue at 80 bar, combined with the gas spring stiffness that effectively turns trapped air into a solid wall, makes the physical execution of this specific design disproportionately risky compared to maturing offshore alternatives.
It is a profound engineering challenge. There is absolutely no denying that. But I think we both agree, based on the depth of the material, that moving to 800 meters completely changes the class of the machine. It forces us to stop thinking about the ocean simply as a place to float a buoy and start thinking about it as an incredibly dense, high-pressure working fluid.
We absolutely agree on that. The abyssal environment requires an entirely different paradigm of engineering. And to the paper's credit, it recognizes that we cannot just weld this together and drop it in the ocean tomorrow. The true point of convergence here is the necessity of phase zero.
The computational modeling.
Exactly. A rigorous 2-year computational fluid dynamics modeling program is absolutely the only way to objectively prove if the gas spring compliance problem can actually be solved at commercially relevant scales. We need supercomputers to simulate those million cycles before we bend any metal.
Without that computational proof, it remains a brilliant but unverified hypothesis. The intersection of underwater compressed air energy storage and deep-sea structural engineering clearly holds vast potential, but it requires that serious, dedicated development pathway to prove the mechanics can actually survive the math.
It comes back to your opening thought about the balloon. Up here at the surface, breathing is easy. The air moves for us. But down in the abyss, the fluid pushes back with immense, unforgiving force. The ultimate question the Enfield paper poses is whether we can build a mechanical lung strong enough and smart enough to breathe under that crushing weight without shattering.
A perfect way to frame it. There is certainly a lot more to explore in this material, and multiple perspectives are crucial as this technology develops. Thank you for joining us on The Debate.
You know, when we think about harnessing the ocean's power, our minds usually go to these massive waves crashing on the surface, right? But what if the real power isn't in the splash and the crash, but in the immense silent pressure of the deep ocean itself? Well, today we're going to explore a radical new concept that does exactly that. This quote from the concept's author, Zachary David Enfield, just perfectly sets the stage. It forces you to reframe the deep sea. It's not some hostile barrier we have to overcome, but a unique and incredibly powerful resource that's just waiting to be tapped into. And that really leads us to the central question here. What if we could actually take that constant, crushing pressure you find 800 meters below the surface and use it as a massive advantage for generating energy? Okay, first things first, let's get into the core physics that could make this a total game changer. It's all about using depth, not just as a place, but as a design variable, one that literally multiplies the force you can get from the water. So let's look at a direct comparison. On the left, you've got your standard oscillating water column, or OWC. It's a pretty common device where surface waves push water up, compress some air, and turn a turbine. But now look at the right. This is the high bar concept. At 800 meters down, the baseline pressure is already 80 times higher. So when a deep ocean current pushes the exact same amount of water into the chamber, the pressure swing it creates is 80 times larger. And that's the number to remember. 80 times the pneumatic, the air pressure, force. It's the same movement of water, but it yields a vastly more powerful result, simply by changing the operating environment from the surface to the deep sea. Now, it's really important to get this straight. This isn't some kind of free energy machine that's creating power from static pressure. No, the machine uses that immense baseline pressure as an amplifier. It makes every single push of water, every pulse, an incredibly dense and powerful event that you can then convert into electricity. So how would a machine like this actually work way down there in the dark? Well, the whole design is based on 5 interconnected subsystems, and each one is a really clever solution to the unique challenges of operating so deep. First up, how do you capture energy if you don't have any surface waves? The answer is something called the abyssal pulse piston. The intake isn't just some passive hole. It's specially shaped to capture energy from deep currents, and even from these things called internal waves. They're like waves between different layers of water. It organizes all that flow into a powerful, coherent slug of water that acts just like a piston. So that piston creates these wild, chaotic pulses of pressure, which, as you can imagine, isn't very efficient for a turbine. The solution is a pneumatic buffer loop. The best way to think about it is like an AC to DC converter for your electronics. You've got check valves and buffer tanks that take all those chaotic pulses and they smooth them out into a steady, high-pressure flow that the turbine can use super efficiently. Now, this might be one of the smartest parts of the whole design, where they put the turbine. It's not at 800 meters. See, because the energy has been converted into a flow of compressed gas, the turbine itself can sit in a dry shaft, much, much closer to the surface. This is huge. It protects it from that super corrosive, high-pressure environment and makes maintenance way, way easier. And here's another clever little touch, the surface cap. The shaft that houses the turbine ends at the surface with this specially shaped cap. It basically uses the ambient wind, kind of like a chimney, to help pull the exhaust gas out. This could boost airflow by a very helpful 5 to 10%. It's a true hybrid machine. Okay, so this all sounds amazing, but this concept is at the very, very beginning of its journey. To really understand its potential, we have to ground it in the reality of today's engineering and, of course, the economic challenges. The biggest hurdle for all wave energy is cost. I mean, just look at these numbers. Current wave energy is way more expensive per kilowatt hour than established renewables like offshore wind. The entire industry, and that includes this new concept, has to find a way to close this major cost gap if it's ever going to be commercially viable. So where does this stepped pressure concept, the SP-HBWC, fit in? Well, you can see it's right at the bottom, at technology readiness level 1 to 2. That means it's basically a formalized concept on paper right now. But the good news is, it doesn't have to start from scratch. It can build on lessons learned from more mature technologies, like commercial OWCs and underwater energy storage systems. And yeah, the engineering risks, they are substantial. I mean, managing the incredibly stiff gas spring that gets created at 80 bar pressure is the top challenge. The structure also has to survive that immense pressure for over 20 years. The seals have to work perfectly for millions of cycles. Oh, and the whole thing has to be installed and maintained with robots. These are serious problems for sure, but they're not impossible. So given those challenges, what's the path forward? You don't just jump into building something this ambitious. The concept paper actually lays out a very deliberate multi-year plan to prove the technology step by step. The roadmap is really methodical. It starts with 2 years of just computer modeling, no metal gets cut, then a 5-year phase building a prototype at a more manageable depth to make sure the physics works, and only after all that would they build a true deep water prototype, eventually leading to a grid-connected pilot in maybe 10 years or more. This is a long-term, serious research effort. You know, the timing for an idea like this might actually be perfect. It doesn't have to invent everything from the ground up. it can leverage all these advancements happening in other fields: better underwater storage, stronger deep-sea materials, more advanced controls. It's really aligned with where the whole marine energy sector is already heading. Which brings us right back to this final thought. Taking this technology 800 meters deep doesn't make it impossible. It makes it a serious piece of engineering. It elevates the potential from some niche device to a machine that could fundamentally change how we think about ocean power. And really, the question it leaves us with is, what other immense, untapped resources are just waiting for us if we only change our perspective?